Our last section of Chapter 11, 11C, continues on looking at mathematics and the art. So again, those places that we don't typically expect to see math show up. And Section B talked about the three places that we see mathematics in the visual arts, and that's proportion, symmetry, and perspective. And we spent time in Section B talking about perspective and symmetry. Section C talks all about proportion and what we call the golden ratio. So just a quote here says, geometry has two great treasures. One is the theorems of Pythagoras. The other is the division of a line into extreme and mean ratio. The first we may compare to gold. The second we may compare to precious jewels. So just talking about how great this golden ratio, we're going to define here in a second, is in the math world and how many things we can do with it. So what is the golden ratio? The ratio of a length of a long piece to the length of a short piece is the same as the ratio of length to the entire line segment to the length of a long piece. So that's really wordy. Let's talk about what that really means. So for any line segment divided into two pieces, that is according to the golden ratio, and we use this symbol here, kind of looks like a zero with a line through it. It's a Greek letter pronounced phi. So we use phi to represent the golden ratio. The ratio of the long piece to the short piece is approximately 8/5. So the exact ratio is this first portion here next to the phi. 1 plus root 5 all divided by 2, which is approximately 1.61803. It's irrational, so we can't get an exact number. But if we call that about 1.62, we can say, hey, that's about 8/5. So 8/5 is certainly a rounded approximation, but it's a good kind of rule of thumb to use when talking about the golden ratio. And really the golden ratio is what we find to be really appeasing to the eye. We see the golden ratio show up all over the place. One of the ways we use the golden ratio is in terms of what we call the golden rectangle. And the golden rectangle is a rectangle whose side length is 5 times as long as its short side. So long side rather is 5 times as long as its short side. So it's proportioned there using the golden ratio. And we can see that that's something that was done with the Parthenon hundreds and hundreds of years ago when that was built. That again, that seeing of the golden ratio all over the place, not just in new recent architecture, but in ancient architecture, it pops up. So consider the following household items with the given dimensions. Which items come closest to having the proportions of the golden ratio? So we want to compare the standard sheet of paper to a picture frame that's 8 inches by 10 inches, to your high-def television, which comes in many sizes but always has a 16:9 ratio of width to height. And that TV we've talked about before. We measure a TV based on the diagonal, and if we know the diagonal, we can use the 16:9 ratio to find the length and the width. And we've talked about that before. Here's another kind of application of using that 16:9 ratio and our high-def TV to see if it's close to that golden rectangle, to see if it's close to that really appealing shape. So the first one talked about the standard sheet of paper, 8.5 by 11. And if we find the ratio for that, taking the long side divided by the short side, so 11 divided by 8.5, we get about 1.29. And if you remember, our golden ratio was 8/5, about, which is about 1.62. So our paper here, that's what we did here in orange, it's fairly close. We'd say it's about 20% less than the golden ratio. So it's close to that golden rectangle, that really appealing shape, but it's not quite there. Let's take a look at the next one. Next one talked about a picture frame that's 8 by 10, which is kind of like that large picture you would print. That's an option for you. Like my wedding picture is a 8 by 10 and a picture frame on my nightstand. So that's just kind of an idea of the type we're talking about here. So again, let's go ahead and find that ratio with the sides of that 8 by 10 picture frame by taking 10/8, and we get 1.25. That was our picture frame. So that's even further from our golden ratio. We want to get closer to about 1.6, and we're a little bit lower, 1.25. We're 23% less than the golden ratio. So we know at this point the paper is closer than the picture frame. The last one we have to compare is our TV, which is that ratio of 16:9. And if we divide 16 by 9, we get about 1.78. That was the high-def television. And remember we said our golden ratio was 1.62, 1.78. That's only about 10% higher. That is our closest to that being the golden rectangle, to having that golden ratio, making it the most appealing to the eye. So of those things, if I had to take a guess before I had done this, that's what I would have guessed, since that's what's so produced as something that should be appealing to the eye, we see that it is closest to our golden ratio. All right, next example, find the length of the shorter side of a golden rectangle is 47 hundredths of a centimeter. Find the length of the longer side. So when we're using the golden ratio, we're finding the golden ratio, we said we should be able to take the longer side, x, over the shorter side, and that will give us the golden ratio, which we call phi. So let's plug in what we know. I know the shorter side is 47 hundredths. I'm looking for the longer side. So x is going to stay my variable. My short side becomes 0.47. And we defined phi to be about 1.62. So now I've got one variable, one equation I can solve. I'm going to multiply both the left and the right side by 0.47 to get that by itself. And x is about equal to 0.76. 1.62 times 0.475 is about 0.76 centimeters long. That would be the length of a long side that would satisfy the golden ratio. If I had a picture frame that was 47 centimeters by 76 centimeters, which doesn't make sense because it's very small, but that would be satisfying the golden ratio. Another look at seeing that in nature is what we call the logarithmic spiral. And a logarithmic spiral, begins with a golden ratio that's divided to make a square on the left. And that's what we see here in picture A. We have a golden ratio, so then our long side divided by our short side is about 1.62, and then we've cut it so that we have exactly a square on the left. Then the process is repeated in each successive golden rectangle, and a spiral is created by connecting the corners of the square. So what they've done here is now they've taken this golden ratio that remains, or golden rectangle rather, on the right, and made a square. And then that creates another golden rectangle, chopped it off into a square, creates another, and so on. And as we could repeatedly do that, if we connect a curve from each of the corners of those squares, we get what's called the logarithmic spiral inside of that golden rectangle. And you can see here on the far right, that shell that we find in nature actually follows that exact logarithmic spiral. So we actually do see these things pop up all over the place, and things that we don't have a hand in, things that occur naturally, which I think is just really neat. The last thing we want to talk about when we're looking at the golden ratio and proportion is what we call the Fibonacci sequence. And we're not going to do a whole lot with it in this chapter in terms of using it to find numbers. More so, I just want you to become familiar with it. If you do continue to take math classes up through the calculuses, you will be using the Fibonacci sequence. You'll be talking about ways of creating an equation for it and so on and so forth. In this case, I just want you to know what it is and that it exists. And the Fibonacci sequence is a sequence that continues to grow with the following pattern: 1, 1, 2, 3, 5, 8, 13, 21, so on. And how that pattern is formed is by taking the previous two terms, adding them together to get the third term. So 1 plus 1 gives us 2, 1 plus 2 gives us 3, 2 plus 3 gives us 5, 3 plus 5 gives us 8, and so on. And that's this is what we call recursive formula here. The next term is defined by the previous term added to the term before that. So an example of the Fibonacci sequence is the population here of rabbits. Beginning of the month, we have one pair when they're babies, then they become adults, and then if each pair has a baby, we're creating what's called the Fibonacci sequence, and we're we're adding the previous two together each time. That's just an example of using that Fibonacci sequence. Now, why do we care about that in terms of the golden ratio? Well, if we take that sequence and we divide a number to the term in front of it, so 2 divided by 1, 3 divided by 2, 5 divided by 3, 8 divided by 5, and so on. And they've done that here for the second term through the 17th term. And hopefully you're noticing that these numbers are getting very, very, very close to the golden ratio. So just another example of that specific number, about 1.62, showing up time and time again. So you do have a writing assignment this week that talks about Fibonacci's sequence. So you're going to do a little bit more research on that on your own. If you have any questions about proportions and the golden ratio, please let me know.